You are watching the Daily Science Journal, where we make complex science topics easy. Subscribe to us, it's absolutely free. Imagine a world that is an exact copy of our own, a perfect reflection. It has stars, planets, maybe even life, just like ours. But there is one tiny, crucial difference. Everything in that world is made of something else, something opposite. This isn't just a fantasy from a comic book. This is the world of antimatter. It's a real substance, a mirror image of everything we know and touch. Every particle in our universe, from the smallest electron to the most massive star, has a twin, an anti-twin. This anti-twin looks and acts almost exactly the same but carries an opposite charge. It is the universe's other self. This idea might sound like science fiction, but it is a fundamental part of modern physics. Antimatter is not just a theory. It is a physical reality we can create and study on Earth. For every electron, there is a positron. For every proton, there is an antiproton. They are identical in mass, but opposite in every other way that matters. Think of them as matter's long-lost siblings, separated at the birth of the universe. They are the yin to our yang. The universe loves symmetry. It loves balance. So it created two versions of everything, one for our world and one for a world that seems to have vanished. So where is all this antimatter? If every particle has an antiparticle, shouldn't there be an equal amount of both? We look out into the cosmos with powerful telescopes and sensitive instruments, and we see galaxies made of matter. We see stars made of matter. We see planets, asteroids, and cosmic dust, all made of the same stuff we are. The universe appears overwhelmingly dominated by matter. The antimatter is missing. It's as if half of creation simply disappeared, a cosmic mystery puzzling scientists for nearly a century. This absence is one of the most profound questions in science. The story of antimatter is a journey into the heart of existence. It forces us to ask the biggest questions. Why are we here? Why is there something rather than nothing? The search for antimatter is more than a scientific quest. It is a search for our cosmic origins. It's a detective story on the grandest scale, clues scattered across space-time. The universe has left us a puzzle, and the first step to solving it is to understand what this mysterious mirror stuff truly is and why it holds the key to understanding why our universe exists at all. The story begins not in a laboratory filled with strange machines, but in the mind of a brilliant physicist. His name was Paul Dirac. In the 1920s, he was working with equations that described the behavior of electrons. But his math told him something strange, something impossible. The equations predicted not one, but two kinds of electrons. One was the familiar particle we all know, with its negative charge. The other was something new, a particle with the exact same mass, but with a positive charge, an anti-electron. At first, Dirac was hesitant. Was it just a mathematical ghost, or a clue to deeper reality? His equations were a window into a hidden aspect of the cosmos. They suggested that for every kind of particle, there must be a corresponding antiparticle, a perfect opposite. A few years later, in 1932, Carl Anderson studied cosmic rays. He watched particle tracks in his detector and saw something incredible, a track curving like an electron but the other way. It was Dirac's ghost, the positron. Humanity had its first proof of antimatter. This opened a Pandora's box of cosmic questions. The most important and dangerous one. What happens when matter and antimatter meet? Total annihilation. When particle meets antiparticle, they vanish in a flash of pure energy. Not a chemical explosion like dynamite. Not a nuclear explosion like a bomb. Far more powerful. 100% mass converted to energy, as E equals mc squared predicts. In the Big Bang's first moments, the universe was a hot, dense soup of matter and antimatter. They were born and annihilated in equal measure. Then a tiny imbalance, a slight preference for matter, tipped the scales. For every billion pairs destroyed, one matter particle survived. That lonely survivor became everything we see today. You, me, the Earth, the stars, we are the lucky ones. And the mystery is why. If you want to study antimatter, you have to create it yourself, right here on Earth. To do this, scientists use massive machines called particle accelerators. Here, physicists take ordinary particles, like protons, and use powerful electric fields to accelerate them to incredible speeds, very close to the speed of light. The next step is to smash them into something. Scientists aim this high-speed beam of protons at a target, usually a block of dense metal. The collision is immensely violent. The energy of the impact is so great that it mimics the conditions of the early universe for a fleeting instant. The raw energy of the collision materializes into a shower of new particles. Out of this maelstrom, for every million or so particles created, you might get one antiproton. The challenge is not just to create them, but to catch them. Scientists have become modern-day alchemists, turning pure energy into tiny specks of antimatter. The amount of antimatter ever created by humans would barely be enough to power a light bulb for a few minutes. To study antimatter, you first need to tame it. The device, a penning trap. They are ghosts in a cage of invisible forces. Inside these traps, scientists can hold antimatter for months. That time lets them perform experiments, like making antihydrogen and checking whether it is a perfect mirror of hydrogen. While scientists are busy making antimatter on Earth, others are looking for it in the cosmos. One of the most ambitious experiments is the Alpha Magnetic Spectrometer, or AMS. As the station orbits the Earth, the AMS sifts through the billions of cosmic ray particles that pass through it every year, distinguishing matter from antimatter. It has found far more positrons than our current theories can explain. This surplus could be a clue to some new, unknown source of antimatter in our galaxy. It might sound surprising, but antimatter is already being used in hospitals around the world, every single day, in positron emission tomography, or PET scans. A patient is given a small dose of a special radioactive sugar. This sugar contains an element that emits positrons. As the tracer decays, it releases positrons. Almost immediately, they bump into an electron and annihilate each other in a tiny, harmless flash of energy. This annihilation produces two high-energy gamma rays that shoot out in precisely opposite directions. The PET scanner is a ring of detectors that records these events. By recording millions of these events, a computer can reconstruct a detailed map of where the tracer has concentrated, allowing doctors to pinpoint tumors or diagnose neurological conditions. It is a beautiful and unexpected gift, turning the concept of annihilation from one of destruction to one of healing. When we dream of traveling to the stars, we need a much more powerful energy source. This is where antimatter enters the realm of future possibility. This energy could be used to heat a propellant to extreme temperatures, creating a powerful rocket exhaust. An antimatter engine would be so efficient that a spaceship could accelerate to a significant fraction of the speed of light. A trip to Mars could be completed in weeks. Of course, the challenges are immense. We would need to produce and store antimatter on an industrial scale, far beyond our current capabilities. We arrive now at the biggest mystery of all. The Big Bang should have created matter and antimatter in perfect, equal amounts. But we are here. We look out into the cosmos, and everywhere we look, we see matter. It seems that for every billion pairs of matter and antimatter particles that annihilated each other, one single matter particle was left over. We are the improbable leftovers of a universe that should have canceled itself out. So, where did all the antimatter go? To solve this mystery, scientists believe three conditions had to be met, first outlined by Andrei Sakharov. Baryon number violation, which states, there must be processes that change the net number of baryons, like protons and neutrons, in a system. The second condition, C-symmetry and CP symmetry violation. Matter and antimatter are not perfect mirror images. That subtle difference could produce slightly more matter over time. The third one, interactions out of thermal equilibrium states. The universe must have undergone periods where it was not in a state of perfect thermal equilibrium. This search drives experiments at CERN, the hunt for proton decay in deep mines, and the search for clues in the faint afterglow of the Big Bang. We are searching for a crack in the mirror of reality, a flaw in the symmetry that allowed the universe and us to exist at all. The story of antimatter is a testament to human curiosity. It began as a whisper in mathematics and is now a substance we can create, trap, and use. And yet, for all we have learned, the biggest questions remain. These are the questions that will occupy the next generation of scientists. The missing antimatter is not just a scientific problem, it is a philosophical one. Its absence is the reason for our presence. The puzzle of antimatter is the puzzle of creation itself. The journey to solve it is one of the grandest adventures we can embark upon. The adventure continues. If you enjoyed this video, please subscribe to our channel for more amazing science stories.